So as we talk about liquids and we talk about them in the context of the kinetic molecular theory, let's remember that kinetic molecular theory is the dominant theory of matter in all of science. And let's think about what theory means in science. What does theory mean in science? Is that kind of like a no big deal, or is theory a pretty big deal?
Pretty big.
Theory is a pretty big deal. So we talk about hypotheses that people may have related to how things work. And a hypothesis is sort of a working explanation. It's the best understanding we have so far. If you have a hypothesis that's like the leading hypothesis about something, which for many years, it was the kinetic molecular hypothesis. And, you know, all the evidence, there's really been nothing that would point to the kinetic molecular hypothesis being incorrect. So the kinetic molecular hypothesis, over time, as nothing seems to poke big enough holes in it to say, yeah, that doesn't work, we say, yeah, this seems to be how it works. So now we have the kinetic molecular theory of matter. So if we think about liquids in terms of kinetic molecular theory, in a liquid, the particles, the actual molecules of the liquid, are much closer together. Because remember we said in gases the particles are very far apart relative to their size. So imagine two tennis balls, one in Chicago and one in Lisbon. That's gas molecules. They're very, very, very far apart relative to their size. With liquids, we're starting to get tennis balls that are all in Ohio. So relative to their size, they're pretty darn close together. So the particles are much closer together, and hence, what do we have acting between them? What do we have when we've got particles that are close together? We have attractive forces. Those particles are all going to be attracted to one another. And because they're all attracted to one another, they tend to stick together. There are a couple different attractive forces that we'll talk about briefly. Do you remember any of the attractive forces between particles that we talked about with gases? One that's especially fun to say, one that I especially enjoy saying. Van der Waals. So we have van der Waals forces. The big ones, though, with liquids are hydrogen bonds and dipole-dipole forces. So, in a substance that is polar, what is true about a polar substance? We talked about this way back in Chapter 6 with atomic structure. We talk about water as being polar. We have our little Mickey Mouse water that we draw where we've got oxygen, two hydrogens, and that picture says it all about why water is polar. How can we tell from that picture that water's polar? What's true? So a polar molecule is something that has got areas of partial charge. And in a water molecule, the bottom end of the molecule, this oxygen chin, oxygen's really electronegative, right? What does that mean? It tends to be an electron hog. It tends to sort of pull more of the electron cloud to it. Hydrogen is not electronegative at all. So more of the electron cloud ends up down here, which means we end up with a region of a partial negative charge on one end of the molecule. And relative to this region, we don't have very many electrons up here. So those hydrogen atoms end up being largely not quite naked protons. They're still surrounded by an electron cloud, but there's much less electron density around them. So that gives you a polar molecule. Well, what happens if you have two polar molecules together? Then what you end up with are these forces of attraction between the negative end of one and the positive end of the other, because opposite charges attract. Those are dipole-dipole forces. So you've got a molecule with a dipole. Di means how many? Two. So you got two poles, a positive and a negative, A dipole-dipole force are those little forces of attraction between the charged parts of a particle. Okay. So one of the names that we give to liquids, we classify liquids as fluids. Okay? And it's important to know the following. Okay, so the important part to remember is that all liquids are fluids, but not all fluids are liquids. Okay, so that's why I've drawn this picture. If it is a liquid, it's considered a fluid. What's the other category of matter that we call fluid? Gases, right. So gases and liquids together comprise the fluids. So all liquids are fluids, not all fluids are liquids. And all that we mean when we say that something is a fluid is that the molecules of that substance are able to flow past one another. So in a gas, in the air around you, the soup of gases around you, those molecules flow past one another. They move freely because there are low attractive forces. In a liquid, we have more powerful attractive forces between molecules than we did in a gas, but they're still sort of loose enough. They're not in a fixed position that those molecules kind of dance around one another. And if you can imagine two people dancing where they may be moving very close to one another, they may, be linked by arms or arms around one another at some point, but they can move past one another, they can flow. Those are the kinds of bonds we're talking about here. They're loose enough to allow those molecules to flow and move. Okay, so now we'll talk a little bit about the properties of liquids as a whole. They have higher densities than gases, and you would expect that. If you think back to our analogy of gases being large numbers of particles very far apart, well, that's low density by definition. Your mass is spread out over a very large area. In a liquid, your mass is in a smaller area. So your mass per unit volume is going to be greater. So this liquid is going to have a higher density. Okay, and we would guess that. You can't really compress a liquid. There is some limited amount of compression that's possible, but not anything like the degree to which we can compress gases. So with gases, we talk a lot about volume and pressure because we can put a gas under pressure. We can take a gas that's occupying a room full. We can take all the air in this room and compress it down into a tiny little cylinder. We can't do that with a liquid. There is some limited amount of compression that's possible, but it's very minimal. Give me an example of a liquid that you can think of that's under pressure. So somebody said pop. We've got our little 2-liter bottle of pop right here, and we think that this is a liquid under pressure. Is it? Okay. What all is in a bottle of pop? Water, sugar, artificial coloring, CO2. What's actually being compressed?
CO2.
The gas. The liquid, you got it. The liquid is really not being compressed. The gas that is dissolved in the liquid is what's being compressed. And when you open it up, you relieve the pressure, and the gas comes out of solution. You get bubble, bubble, bubble. Okay.
The same thing, how could one be compressed and not the other?
Because liquids are not tremendously compressible. That's how. Because within that, with
a certain amount of pressure, wouldn't there?
there is, but the liquid itself is not really being compressed. The gas within the liquid is being compressed. Yes, technically the liquid is under some amount of pressure, but it's not being compressed. I now want to talk a little bit about phase changes with you. You have all known since, I don't know, first grade, third grade, something like that. Water freezes and it becomes a solid. Water thaws Ice thaws and it becomes a liquid. So you know the basics. You know what those changes are called. You know that going from a solid to a liquid is called melting or thawing. You know that going from a liquid to a solid is called freezing. What's it called when a liquid becomes a gas? Okay, evaporation. And we have another term that we use. Have you ever made pasta at home? Boiling? But yes, the more technical term is vaporization. We vaporize something. So you can evaporate something, you can vaporize it. My question for you is there a difference between evaporation and boiling? Okay, so we've got two different little hypotheses running here. We've got boiling means that there are bubbles, and evaporation is magic. Okay? It just disappears. You don't see bubbles. You don't see gas leaving the water. And how did you sum that up? That evaporation has to do with the water itself, while boiling has to do with some kind of gas. Okay. I want you to pay attention to a word that is trapped inside the word evaporation. Vapor. So both evaporation and boiling involve water molecules that are formerly liquid, leaving the liquid, escaping the bounds of their liquidness, and jumping up into the air and becoming water vapor. Okay? Both of them involve that. As was mentioned, boiling involves tiny bubbles. That's true. In evaporation, we'll X out magic, but you don't see any little bubbles. It does seem like magic. You don't see bubbles of water vapor leaving the liquid, do you? It just sort of happens slowly. If you leave a glass of water on the windowsill, 2 weeks later, it's all gone. It evaporated. Okay. Evaporation involves the movement of water from liquid to gas below the boiling point. You're not at the boiling point of the liquid. The liquid is not boiling. Yeah, evaporation is the transfer of water molecules or liquid molecules from liquid to gas state, not at the boiling point. So this is by definition in a non-boiling liquid. All of the gas particles, all the liquid particles that escape and become gases in evaporation come from the top of the liquid. In evaporation, they come from that line where the liquid meets the gases above it. They come from the surface. Okay? In boiling, and when you boil a pot of water at home, where's the first place you see bubbles? On the bottom of the pan. In boiling, you're at that critical temperature for a substance where it's what we call the boiling point. And those particles are escaping from the liquid phase into the gas phase within the liquid. So they're actually not just leaving at the surface, they're leaving from down inside the liquid. Hence why we see all those little tiny bubbles as suddenly they pop out of being liquid, pop into being gases, and they show up as bubbles. Okay? That's one phase change. The other one we talk about freezing or solidification. That's when we go from being a liquid to being a solid. So these are the two directions we can go. These are the two directions we can go from a liquid, and let's draw that up. If I have something that's a liquid, it can either become a gas or it can become a solid. This depends on both its pressure and its temperature. The amount of pressure on the liquid will help to determine at what temperature it can become a gas. So let's identify these processes real quickly. So if we're going to go from a liquid to a gas, we call that vaporization. There are two specific cases of vaporization. One is evaporation, which is pretty passive. It's much slower. It occurs below the boiling point of the liquid. The other is boiling, which is not passive at all. We're adding energy to the liquid. We're freeing those liquid molecules, and they're taking off and becoming gases. What about going the other direction, becoming a... So yeah, if we go from a liquid to a solid, we call that solidification or freezing. Any other comments or questions about liquids? That's about all we're going to do to start off talking about liquids. We'll break the notes here, and then we'll go on to talk a little bit about solids. Anything? Okay.